Hello. This is the presentation of the poster titled Comparative Study of Acidic and Basic Catalysts for Sol-Gel Synthesis of Monodisperse Silicon Dioxide Nanoparticles AS Nanofillers in Epoxy Composites. I will walk you through the key findings and results. Silicon dioxide, or silica nanoparticles, are among the most widely studied inorganic nanomaterials due to their remarkable thermal stability, chemical inertness, large specific surface area, and excellent compatibility with organic polymers. These properties make them highly attractive for applications in catalysis, drug delivery, coatings, optical devices, and particularly as reinforcing agents in polymer matrix composite materials. The Sol-Gel process offers a low-temperature, versatile route to synthesize silica nanoparticles with precise control over particle size and morphology by simply varying the catalyst and reaction conditions. The objective of this study was to synthesize amorphous silica nanoparticles using 3 different synthesis routes, each employing a distinct catalyst, and to compare the resulting particle characteristics through multiple complementary characterization techniques. The Sol-Gel synthesis was carried out using tetraethyl orthosilicate, known as TEOS, as the silicon precursor, with ethanol as solvent and water for hydrolysis. 3 catalytic routes were explored. Route A used glacial acetic acid as catalyst, Route B used a dilute 0.16 molar acetic acid solution, and Route C used a 30% ammonia solution. In all routes, hydrolysis and condensation reactions were carried out at room temperature, followed by aging, drying, and finally calcination at 700 degrees Celsius for 2 hours to obtain the final silica powder. Now let us look at the characterization results. Fourier transform infrared spectroscopy, or FTIR, confirmed the formation of the silica network in all 3 routes. The spectra show the characteristic asymmetric stretching vibration of the silicon-oxygen-silicon bond at wave numbers between 1085 and 1111 inverse centimeters, and the symmetric stretching at 802 to 805 inverse centimeters. These bands are the definitive fingerprint of an amorphous silica structure and confirm that the Sol-Gel condensation reaction was successful for all 3 catalysts. X-ray diffraction analysis further confirmed the amorphous nature of the synthesized nanoparticles. The diffractograms display a broad halo centered around 22 degrees 2 theta for routes A and B, with no sharp crystalline peaks present. This broad diffuse scattering is characteristic of amorphous silica and indicates that the calcination at 700 degrees Celsius did not induce crystallization. Field emission scanning electron microscopy images, along with particle size distribution analysis, revealed important differences between the 3 synthesis routes. Route A, using glacial acetic acid, produced nanoparticles with an average diameter of 36.41 nanometers and a standard deviation of 2.62 nanometers. Route B, using dilute acetic acid, yielded smaller and more uniform particles with an average of 27.44 nanometers and a standard deviation of 2.22 nanometers. Route C, using ammonia as the basic catalyst, produced the smallest particles, averaging 25.63 nanometers with a standard deviation of 1.97 nanometers. This trend clearly demonstrates that the catalyst type and concentration directly influence the nucleation and growth kinetics of the silica particles during condensation. In conclusion, this work successfully demonstrates the synthesis of amorphous silica nanoparticles via the Sol-Gel method using 3 different catalyst systems. All routes produced nanoparticles with spherical morphology and amorphous structure, as confirmed by FTIR and XRD. The catalyst plays a critical role in determining particle size. Acidic conditions with glacial acetic acid produced larger particles at 36 nanometers, while dilute acid and basic ammonia catalysis produced progressively finer nanoparticles down to approximately 26 nanometers. The narrow size distributions observed in all routes indicate good process control. These results confirm that the Sol-Gel method is a robust and tunable approach for producing silica nanoparticles, and the obtained materials hold significant potential as nanofillers in polymer composites and other advanced material applications. Thank you for your attention. I hope this work contributes to the understanding of nanoparticle synthesis by Sol-Gel and opens pathways for future optimization and application of these materials.